Hey everyone, welcome to Math 482 Winter Quarter 2021. We finally got through 2020. I wish I could see you all face to face. It's unfortunate. I really love teaching this class and I wish we could be in the classroom together, but we're all used to this virtual thing at this point, so we're just going to get through it as best we can. And so let's get straight to the math. Remember, last quarter we studied groups. A group was a place where there's a notion of multiplication. Right? And you can think of it as sort of the bare bones place where a notion of multiplication made sense, right? We had a set together with three axioms, a set together with a notion of multiplication, a binary operation, along with three axioms that made the arithmetic actually made sense, right? Associativity, identity, and inverses. and one of the sort of first examples that we looked at when we were talking about groups was the integers. And I said, well, with integers, there's addition, and that's our binary operation. We also studied the real numbers and the rational numbers, the complex numbers. Those were also familiar sets where a notion of generically we would call it multiplication, but in those settings, right, it was actually addition was our operation. And when we were doing that, right, so for example, we were working with the integers. Remember this ordered pair notation right here. So this is the group of integers together with the operation of addition, right? And so we would add our integers together, and that was our operation. Same thing with the real numbers, rational numbers, and so on. But I suspect, right, in the back of your heads, you're saying, all right, fine, we can do arithmetic in the integers by doing addition, but there's also multiplication, right? And really, when we do arithmetic with the integers, we kind of go back and forth, and interchangeably, we use addition and multiplication. Same thing with real numbers, rational numbers, complex numbers. And so, in this quarter, what we're going to do is we're going to study objects. They're called rings. And a ring is a place where you have two operations, right? We'll call them addition and multiplication. And we are going to study this. We're going to generalize the true properties, the true arithmetic properties of the integers now, right, into this object called a ring. So, in your book, we will be in chapter 18, and this is called Rings and Fields. And so we're going to start off with the definition, and this is going to be the primary object of study in this quarter. It's called a ring. So a ring is a triple, which I'll write is R, comma, plus, comma, dot, where R is just a set. So R is a set. Plus and dot are going to be binary operations on R. So plus and dot are binary operations on R, which we give them names automatically. I'm going to call this one addition, and dot is going to be called multiplication. So we'll say called multiplication. Oh, I'm saying these backwards. Sorry, it's called addition and multiplication. So called addition and multiplication. Respectively. And I should be underlining the terms here. So the ring is the thing we're defining. There's also the names addition and multiplication corresponding to our binary operations. Subject to the following axioms, right? So respectively, such that the following hold. All right, so our first axiom is that R comma plus, right, the group consisting of R together with the binary operation of plus. So this is an abelian group. The second axiom is that dot is associative. All right, so we don't expect R to be a group with respect to the multiplication. And if you think about, right, so remember, we're trying to generalize the idea of integers, right? So if we look at Z, it's a group under the operation of plus, of addition, but it's not a group under multiplication, right? There's no inverses. But it is associative, right? So multiplication is associative when we work with the integers. So we're trying to generalize this idea. And then there's one more axiom, and this axiom connects the two operations together. So we'll say for all A, B, and C in R. And there's really two parts to it. So I guess let me just call them, I don't really need to call them A and B. There's two parts to axiom 3. So the first one, A plus B dot C is equal to A dot C plus B dot C. This is called right distributivity. So, and there's also left distributivity. So that would be A dot B plus C is equal to A dot B plus A dot C. So that's the left distributive property. All right, so that's a bit of a mouthful, but this is what a ring is, right? It's a place where we have two operations, and it really generalizes our familiar notion of how we do arithmetic when we're dealing with the integers, right? Under addition, we've got an abelian group. Under multiplication, we have associativity, and then there's this connection between the two, the distributive properties, that say, all right, if you want to add and then multiply, it's the same as multiplying and adding the corresponding results, right? And it works on both the left and the right. Okay, so that's a ring. Remember, when we were dealing, when we learned about groups, we kind of kept this ordered pair notation for a little while, but eventually we said, you know what, let's just say let G be a group, and it's understood that there's this operation, right? We don't use the dot anymore. Same thing, we're not gonna use this triple notation unless we absolutely have to avoid some sort of confusion. And so that's the first thing we're going to say is, right away, we'll just say, so let's say note. Well, okay, yeah, so when no confusion will arise, we drop the ordered triple notation. Ordered triple notation, and in which case we'll just say that R is a ring. We'll say R is a ring, and so it will be understood that when we say the words R is a ring, that there are these two operations, plus and dot, so addition and multiplication. So it will be understood that R is equipped with plus and dot subject to axioms 1 through 3. Also, just as when we were working with a group, unless we absolutely had to, we didn't write A dot B, right? If we needed to keep, if we had a couple of different operations running around and we want to keep them separately, maybe we use some symbols. But typically, for multiplication, we just use juxtaposition. And that's the standard thing to do when you're working with rings. You will use the plus, right, when you're working with addition, but multiplication will be denoted by juxtaposition, just as we do when we're multiplying integers or real numbers or whatever. I guess I'll put it here. So this is still under the note, right? This is really just sort of establishing the standard notation that we'll use when working with rings. So, how do I want to say this? Oh, yeah, let me just put it over here. So rather than using dot for multiplication, we use juxtaposition. Juxtaposition, right? We just want to simplify the notation as much as possible, and we're already familiar with doing these kind of things when we're working with groups. Okay, so let's get some examples now. So first, so under the usual notions of multiplication, or addition and multiplication. Z, Q, R, and C are rings. Another example, if R is any ring, let M sub n of R be the set of n by n matrices with entries in the ring capital R. So remember, last quarter we did this, M sub n of the real numbers, but it turns out you can actually form the set of all n by n matrices where instead of requiring the entries to be real numbers, the entries can be any ring. So under, and so in particular, if we want, we can put Z here, right? The group, or the ring, I'm about to say this, that this turns out to be a ring, right? But we can put Z here and consider the set of n by n matrices with entries in Z. Okay, so under the usual operations of matrix addition and multiplication, M sub n R is a ring. So you can go through and check this. And oh, and here's one thing to notice. Axiom 2 says that dot, right, multiplication just needs to be associative. We said that when we're talking about a ring, right, so we have R, comma, plus, comma, dot, and we require R plus to be an abelian group, right? So addition is always going to be commutative. But all we said about dot is that it needs to be associative. So it may or may not be commutative. In particular, or for example, or what am I trying to say here? Here is an example where multiplication is not commutative. So you should say note. This is an example where multiplication is not commutative, right? So addition will always be commutative when we're working with rings. Multiplication maybe, maybe not. Okay, here's another example. So let's let capital G be an abelian group and let, it's usually denoted end G, so end of G. So let this denote the set of homomorphisms. Well, it's really the it's the set of endomorphisms of G. So let's say set of endomorphisms of capital G, where remember an endomorphism is a homomorphism from G to G. So let me just say that in parentheses here. So this is homomorphisms. From G to G. So take the entire set of homomorphisms from G to G, where all it requires is that G is an abelian group. Now what we're going to do is we're going to put some operations on this set, right, the set of endomorphisms that actually turns it into a ring. So for, let's say, phi and psi in end G, define, so I need to define addition and multiplication. So we're going to define phi plus psi of little g equal to phi of G plus psi of G. So what am I defining right here? I'm defining that operation, the operation of addition of endomorphisms. And how do I specify it? Well, okay, so phi plus psi is supposed to be an endomorphism of G, which means I need to tell you what it does to an element of capital G. Well, what it does is this over here on the right-hand side. Plug little g into both phi and psi and add them together, and we should be careful here. That right there is the operation in capital G. So I'm defining plus, right? This operation right here is the operation that we're going to have on the set of endomorphisms. But it's defined in terms of this operation right here. And also, so we'll say and phi psi, so multiplication. Well, I don't even need to specify this. This is going to be composition. So phi of psi. So we show, and I'll actually go through the details here. So we show that end G is a ring called the endomorphism. The endomorphism ring. Endomorphism ring of capital G. Okay, so in the first ones I just said, like for example, the real numbers, you can go and check the details if you like. Same thing with the matrices, but here I'm actually going to go through the details. So, what do I need to do first? Well, what do I need to do? I need to check the axioms, right? We have actually defined a couple of binary operations here. Well, I guess I need to actually be clear that these are binary operations. So, yeah, so for the first one, so we show that end G comma plus is an abelian group. And so what do I need to do? I need to show that this new object right here actually is a homomorphism from G to G. So, let's let phi and psi be in end G, and let's let little g and little h be in capital G. Then, phi plus psi of G plus H. Okay, so according to the definition, that's going to be phi of G plus H plus psi of G plus H. So I'm using this formula right there. But now, remember, both phi and psi are homomorphisms, so I can split this up and then move things around, right? So this is equal to phi of G plus phi of H plus psi of G plus psi of H. And so let's see, what is this? So now I'm going to move things around a little bit. So let's do, this is phi of G plus psi of G plus phi of H plus psi of H. I'm using associativity of addition in capital G to move these things around and put them, group them as I like. Now what's this? Well, this is phi plus psi of G, and this one is phi plus psi of H. So what does that tell us then? Therefore, phi plus psi actually is a homomorphism from G to G, so that means that phi plus psi is an element of end capital G. In other words, end G is closed under addition. So that is end G is closed under plus. Okay, so now we need to show associative. What am I going to call them? I'm going to call them alpha, beta, and gamma. So given alpha, beta, and gamma in end G and little g in capital G, note that alpha plus beta plus gamma applied to little g is equal to, so what's this going to be? Alpha plus beta of little g plus gamma of little g. And now you can probably see what's going to happen, right? So now this is equal to alpha of g plus beta of g plus gamma of g. Now I can use associativity of plus inside g. So this is alpha of g plus beta of g plus gamma of G. And then I can put everything back, so this is alpha of G plus beta plus gamma of G. And then that is going to be alpha plus parentheses beta plus gamma of G. So what that tells us is so I can say, therefore, alpha plus beta plus gamma equals alpha plus beta plus gamma. What I did is I showed that this function right here and this function right here do exactly the same thing to an arbitrary element of the domain, which means as functions they're equal to each other. Okay, now we need an identity. So, all right, we've shown associativity. Now we need an identity. So let's define, let me call it little epsilon from, this is going to go from G to G by epsilon of little e, epsilon of little g equals little e, the identity for all little g in capital G. So this function epsilon takes each element and spits out the identity in G. So note that epsilon definitely is a homomorphism. You can check the details there, but note that epsilon is an element of end G. And if, let's say, phi is an element of end G, then phi plus epsilon applied to little g is equal to phi of g plus epsilon of g, which equals phi of g plus little e, which equals phi of g. And so phi plus epsilon equals phi. And similarly, if you did it in the opposite order, so similarly, epsilon plus phi equals phi. So what we have is this function epsilon behaves as the identity in the group of or I guess I haven't quite shown it's a group, but in end G. Okay, so in fact, let's recap that. The trivial homomorphism, trivial homomorphism is the identity in end G. Last thing we need is inverses. So for phi in end G, define a new function which is going to be called or written minus phi. That's going to go from G to G by minus phi of G equals the obvious thing, negative phi of G. And let's put parentheses here to be clear. So what are we doing? We're defining a new function and we're going to use the symbol negative phi. How does it work? It works by taking an element G and associating to it the element, the inverse in G. So this is, well, let's say this is the inverse in G, right? So this phi of G is an element of capital G, which means it's got an inverse. That inverse, because we're working in abelian, we're writing additively, it's denoted negative G. Sorry, negative phi of G. And we can say check that. So let's see now, if it's going to be an inverse, that would mean that phi plus minus phi has to equal our identity, which is epsilon, which is equal to minus phi plus phi. All right, so now we've got inverses. And then the last thing, all right, remember we need to show that R plus is an abelian group. So we'll say finally, let's let say alpha and beta be in end G and little g in capital G. Then alpha plus beta of little g, by definition, is alpha of g plus beta of g, which is equal to beta of g plus alpha of g. Right here, we're using the fact that g is an abelian group, so I can reverse the order here. And then that's equal to beta plus alpha of g. Therefore, alpha plus beta equals beta plus alpha, right? We've shown that this function, alpha plus beta, does exactly the same thing to every element as beta plus alpha. That means that they're the same function. So our conclusion end G comma plus is an abelian group. Well, that takes care of axiom 1. Axiom 2, composition of endomorphisms is an endomorphism so our set end G is closed under multiplication. Right? Remember, multiplication is in this setting has been declared to be composition of functions. Multiplication. Oh, right. So I got to say one more thing. Since composition of functions, they don't even have to be homomorphism, so composition of functions is associative. Axiom 2 is satisfied. Composition is an associative binary operation on end G. All right, there's one more axiom. And that's the distributive properties. And so let's just check one of them. It's just kind of we just got to crank it out now. So let's let alpha, beta, and gamma be in end G and little g in capital G. Then alpha plus beta plus, times, so this is going to be composition. Gamma, a little square bracket here. So this is the function applied to little g. Okay, so how is that going to work? That's going to be alpha plus beta of gamma of g, All right, when I write this right here, this means composition, so we're composing alpha plus beta with gamma. Okay, so now what's this? This is alpha alpha gamma of little g plus beta gamma of little g. Now I'm using the definition of addition, right? So we're applying alpha plus beta to this element right here. And then this is equal to what am I trying to say? Oh, right. This is equal to alpha plus beta. Wait, what do I want to say here? Oh, this is actually all I need, right? Well, okay, let me just say it a little bit nicer. This is alpha of gamma of g plus beta of gamma of g. And so, what do I want to say here? This is so weird. Well, no, here's what I really want to say. This is alpha gamma plus beta gamma of little g. So, okay, so therefore, sorry, I got a little stuck there for a second. So therefore, alpha plus beta times gamma is equal to alpha gamma plus beta gamma. Now, okay, there's our right distributive property, the left distributive property. The proof is similar, so we'll say similarly. Let's say alpha times beta plus gamma is equal to alpha beta plus alpha gamma. All right, so that completes the proof. I'm trying to write a concluding sentence. Okay, so we'll say therefore. End G is a ring. So notice there's a lot of work involved in showing directly that you've got a ring, right, when you start off abstractly like that. So that took a little bit of time. Let's see, how long have we been going now? Oh, that's a good place to stop. Today's the first day of classes, and so I guess about 38 minutes, that's plenty of time. Okay, so we'll see you next time. Right.